Then welcome back to COMP526. In the rest of Unit 0, still kind of before the actual topics, I want to discuss a few proof techniques. So these are some mathematical preliminaries that we'll use in the background in the following. It's more a bit about framing the language we try to use if we want to be very precise. And I think it's important that you're able to understand such kind of proofs and read them. We won't usually go to all the level of detail that I'll show you today, but I think it's important to know what that level of detail looks like so that you can recognize it and you can reproduce it if you have to, where things need to be extremely precise. And so the goals for this unit is to learn some templates for proofs, how they are structured to follow the logic of the statements. Specifically, the useful tool of mathematical induction, because much in computer science is about discrete mathematics. Induction is a key tool that's often used. And we'll briefly look at the case where computer science often uses formal proofs. That's for proving the correctness of programs. That last part is not the key topic for this module, but I want to give you a glimpse of it either way. I'll start with a little digression that some of you have picked up already on CampusWire. I'll come back to that. And then we'll go through these things, the general proof templates and induction in a bit more detail, and then how to prove programs correct. I want to start by motivating this a little bit. Hold on, I'm on the wrong deck of slides. Let's try again with this year's date. The rest so far wouldn't have been different. I want to motivate a little bit, apart from just me telling you it's important that you are able to read proofs. I want to motivate a little bit why it's useful to make very formal statements about algorithms. And I want to give you a small example of an algorithm that looks innocent and looks correct. And even if you try it, maybe it looks fine, because it has to do with randomness. And randomness is tricky to pin down with tests, because they come out different each time. Right, so a toy problem. You're given an array of numbers, and you want to put them in completely random order. You want to shuffle them. It's a function that most standard libraries already have, so maybe you don't have to implement one. The point is, this is a simple example that fits on a slide to illustrate the point. So how would you do that? Well, you could say, I pick a random position for each number, and then I swap. Each position in the array gets swapped to a random other position. And by random, I mean a uniformly distributed random number in that range, so that's all good. Once you've done that, pretty much no element is where it was before, and they're all kind of at a random position. So it looks like a sensible way to do. And then maybe before I dive deeper, I'll ask you a bit about this. I'll swip back to the code in a second. Where is my question? I've opened the question on Slido now, but I'll go back to the code so you can take a quick look at that. So note that you can select several things. So we had something like 130, 140 people on the previous Slido calls. So I would hope to see a similar number for this one. While we're waiting, there's two questions on Slido that I might answer. So the lecture today stops before 1. The slot goes until 1, but we started 10 minutes late, so we should be done by 20 to 1 the latest. And the password for Campus Wire is on the announcement on Canvas. Again, 4 digits. I can't be bothered to remember them. So as you can see, we have various statements got votes. Now, around a third or so have trouble reading the pseudocode. So maybe it's worth going over that part just briefly. So this is a kind of pseudocode that is a little similar to many languages and has similarity to Python, but is I tried to use the syntax that is more unambiguous as opposed to more Pythonic. For example, I use this := for assignments because equal always is a bit ambiguous. Is that an equality comparison or is it an assignment? So I'll try to use this for assignment and the double equals for equality comparisons and never the normal equal. So I try to make it a little less ambiguous. And then sometimes there's just things like swap the 2 positions in an array where it's just an English language sentence that if you have some programming language, you probably can translate to how that looks in a concrete language. And OK, here I was just lazy. You could, of course, assign a of I to some temporary variable, then assign to a of I, a of r, and then a of r becomes the temporary variable. That's just a shorthand. And this is a function call where I didn't show you how this is implemented, but let's suppose this is part of the programming library that we're using. And indeed, Python has a library for doing that in the random library, and all languages I know have a way to choose a uniformly random number. So let me show what I marked as the, well, correct for me. The second one is, of course, depending on who answers. And sort of same for this one. It's also true. OK, I mean, so remember, you can change your answer now, and you can make the green bars go all the way to the right. But there's no real point. You don't get extra marks for being correct on those. And it's more interesting to see that a lot of people thought, for example, this answer is correct. Now, if you keep changing the numbers or more people add it, they kind of skew the picture a bit. But the point of these polls is to give you a feeling what the room thinks, and also give me a feeling of what the room thinks. But if that bar goes up, I'm happy. It can generate all possible orderings of the array. That's true, but all the others are not. In particular, it's not really solving the problem we are trying to solve. I'll just demonstrate you briefly why. If you take an array with just 2 elements and you call this function and analyze how likely is it to go each way. So what I'm showing you here is the probability that the outcome is 1, 2, the same order you put things in, or 2, 1. That's the only 2 possibilities with 2 elements. And they're equally likely. Great, so we're on track. But if you start adding more elements, for 3 elements, there's already 3 permutations that are a bit more likely, and the other 3 are a bit less likely. Now, how did I arrive at those numbers? And that relates to the campus wire question. And I want to give a shout out to the campus wire question. It's great that some people experimented with the code, implemented it, and tested it. It's good for two reasons. It means you engage with the material. And the second one, it is nice for me to make the point that randomness is tricky to nail down with tests. Because they implemented the corrected version that I'll show in a second. But if you run the method several times, the outcome is random. And so it's hard to gauge if it's correct or not just from looking at tests. What I did to produce these bars is I basically analyzed the function theoretically and looked at what are all the possible outcomes for the calls to this random method. And this is discrete here, right? It only has n different choices in this case, but you have to do it for every loop iteration. If you go through that and go through all possible options, each has the same probability, but the outcomes are not equally distributed. And things get worse if you go to larger lists. And then I stopped because it spiraled a bit out of control. You have many, many things to try. But I want to point out here, this green bar is the average, or is where uniform should be, 1 over n factorial for n elements. And you see some elements are almost twice as likely, some of the specific orders. So it's not even, it's not just wrong in that it's not perfectly uniform. It seems to get worse with larger inputs. And that's a bit, well, it's a problem if you want it uniform. Now, so don't ever use that code. We discussed that. There's a simple way to fix this, and I'm sure some of you will know this. It's a well-known algorithm. I would call it the Knuth-Fisher-Yates shuffle because all three were involved in. It's maybe basic enough to have been reinvented independently a few times. The only change you really need is restrict the range of this random position, and then it works fine. I don't want to go into detail why it works. That's not really my point in this unit. And it's also not about, this lecture is not so much about random generation. And yeah, there's good Wikipedia articles about this algorithm. If you repeat my experiment, then you see it comes out perfectly uniform. To give you a quick intuition, why the previous method cannot possibly have worked is if you just analyze the number of possible things it can do. It had n iterations and drew 1 out of n choices each time. So that's n to the n different things. But the number of permutations is n factorial, and these two numbers are not equal. And they are even, they're co-prime, so there's just no way this could have worked. In hindsight, maybe this is obvious, or depending on who looks at it, maybe. But that's a quick way to prove the previous code cannot be correct. Doesn't tell you how to fix it, though. But yeah, in this case, it's already been invented, and so we don't have to worry about it. But what's the point of this? My point is the previous code looks quite reasonable. If you read this in a code review, maybe you'd say, yeah, it looks like a good random shuffle. And it looks very similar to this code. So how can you tell them apart with certainty? And again, who guarantees me that I've done this for up to 5 elements? Maybe something wonky happens with 6, 7, or 8 elements. There's too many options for me to try. At the very latest, so maybe 11 factorial is still doable, but 20 factorial is out of the question. It's just too many different things. So there's no way a test will get you to the right answer. So the only thing that's left is a formal proof or a theoretical analysis of the algorithm that can tell you with certainty this one's going to shuffle correctly, right? And that's why we're stressing this in algorithms so much. Many algorithms look reasonable and are just wrong. It's very, very tricky to find the difference, to see the difference.